Hey, good afternoon, everyone. This is Aaron Johnson with AIPG. I apologize for the delay. We've been fighting a technical issue that I suspect is related to the most recent update to Zoom. So we've done the very best that we can to take care of that problem. It's going to be a little different today, so please bear with us. A couple of quick bookkeeping things. If you registered for CEUs, the certificate for your CEUs will be sent to the same email address that you used when you registered for the webinar. If you're taking this webinar for CEUs for use for your registration in New York State, you will need to take a 5-question assessment following the webinar. That assessment is a requirement for the New York State Education Department, and we will have to follow through on that. The assessment will be available after the webinar for about an hour, and we'll put a link to that assessment in the chat. So watch the chat for that link. You can take that assessment as many times as you need to, and you need to get 4 out of 5 correct to be able to receive your continuing education credit. I'm very pleased today to have Ed Winner with us for his presentation. Ed has been Vice President of Remediation Products Incorporated since 2021. Prior to his work there, he was Assistant Director in the Division of Waste Management for the Commonwealth of Kentucky. Ed worked for the Commonwealth in the risk assessment branch starting in 2000, and then in 2007 moved on to the Paducah gas diffusion plant section as supervisor and facilities agreement manager. Ed has a BA from Tennessee Temple University, a BS and PhD from the University of Louisville, so he's a Cardinal, and he was a postdoctoral fellow at the Lions Eye Research Center. It's my pleasure today to introduce Dr. Ed Winner. Ed, the floor is yours.
Okay, thank you. What I want to talk about today is just a few items that are related to activated carbon as an injectate in the subsurface. So I'm going to cover what is activated carbon, the patterns of its distribution upon injection, and evidence of its efficacy. This is the whole activated carbon thing I came to through working with underground storage tanks and became very excited about how well this mode of remediation work. So I'm happy to present this. Let's get on with it. First of all, activated carbon. You take any carbonaceous substance and heat it up to make a char. This is the beginning of how you make activated carbon. The char is then treated with a chemically or physically to produce a series of interconnected holes. You can make activated carbon out of pretty much any carbon substance. The most typical substances are coconut, bituminous coal, lignin, or wood. Depending on which material you start with, you will get different transport structure and you will get different absorption characteristics. Similarly with the activation processes, depending on what activation processes you follow, you will get different transport pores and different absorption kinetics. Sorry about this, guys. This is just a technical weird thing that's going on today. Okay, there are 3 primary means of activating carbon. Most typically, it's done with thermally or heat treated. This would be typical for coals, coconuts, and lignin-based products. There's also chemical activation, which is most typical for wood-based products. And there also are activated carbon products that are produced by what's called reagglomeration. And the way you do that is you grind the carbon down prior to activate or building the char and put it back together, then activate it. The purpose of doing the reagglomeration is you get a more even activation. So the gist of what I want you to get here is that all activated carbons are not the same. They do not absorb equally or have the same affinity for individual chemicals. So these are some electron micrographs And what I want you to look at is wood, which is on the left side. You notice the xylem pores that are still open in the wood post-activation versus coconut on the right, which is very, very tight. And what you find is that coconut has a lot more absorption pores, and we'll get into what these pores are in a moment, but absorption pores are where chemicals would bind, than does wood carbon. And visually, you can almost imagine that just looking at the picture. Thus, if you are trying to absorb some molecules, wood would be preferable to coconut or coconut preferable to wood. Now, the carbon that is here on your left is a coal-based carbon. It's an F400 carbon from Calgon. And you can see that it's magnified to 5 microns. So you see the 5 micron scale in the lower right-hand corner of the screen. Notice how rough and porous the surface looks. You didn't see that in either the coconut carbon or the wood carbon. And here I'm bringing back into the screen and focus the coconut carbon for comparison. And you'll see this, if I had a pointer here, but I'm going to spare myself yet another technical issue. But on the right, you can see a very porous structure in the activated carbon that's coal-based, where on the right-hand side for the coconut carbon, you can see that it appears almost slick in places. Thus, there are different absorption characteristics for these two carbons also. This is a colloidal carbon. The only difference, the core difference you're going to see is if you look at the 5 micron scale on the right-hand side, you'll see that these are very small pieces, most of them less than 5 microns. If you look at the surfaces, you do not see the kind of same surface characteristics you saw in the F400 carbon. Doesn't mean they're not there. It's just during the process of breaking it down into these smaller pieces, it may be obscured. It's hard to say, but I can say looking at this picture that this is a different kind of carbon. It's probably a little bit harder. Maybe that's necessary when you ball mill this to the smaller fraction. So there are some of your carbons. And why are we interested in activated carbon? Because of the adsorption characteristics. If we can absorb the contaminant to the carbon, then you can reduce the contaminant concentration, say, in an aquifer. And that would be a partial kind of treatment, right? Activated carbon itself has a lot of internal pores. If we look at those pores, they are defined as micropores having less than 2 nanometers in diameter. Then the macropores and mesopores. The mesopores are 1 to 5 nanometers in diameter. The macropores are greater than 50 nanometers in diameter. It's the macro and mesopores that are the transport pores that allow a chemical that's being bound to enter into the carbon structure, where the actual place of binding is the micropores. If you look at the diagram to your right, the one that's in purple, I've kind of illustrated the carbon plates, and you can see the molecules kind of binding those carbon plates. And you can also see openings that are transport pores, kind of gives you an image of how the carbon comes together. In fact, the carbon rings are 6-member rings that are laid in plates, kind of like graphite. And I think you've seen graphite. And then just imagine graphite getting into a heavy head-on collision in these 6-member rings, some of them fracturing and turning in different angles. And that's kind of what activated carbon would look like at the molecular level. The binding on these graphite plates within the activated carbon is related to London dipole forces. And those forces don't disappear when, say, you have one butane molecule binding this graphite plate, the next one, kind of like a magnet picking up pieces of iron filings, the next one, the next butane that binds can also bind to the butane before it, and they can kind of stack, so that what you have is not one binding strength for a particular carbon, for a particular contaminant, but within that, you have multiple binding strengths depending on the relationship between the contaminant and the plates around it. So if you look on the right-hand side, I have kind of a blue picture there, and that's meant to illustrate that you have all of these plates that are interacting with the molecule in different angles to cause the binding. Now, this picture is meant to kind of give you the idea that if you have the interaction of all of those plates and the molecules that are interacting with those graphite plates within the activated carbon are at different distances, you can think of this and model it energetically as patches, various areas, and these patches have different energetics as far as how well they bind a contaminant. And since some are good, some are not so good, and most are average, you end up with a Gaussian distribution of binding. So if you look up on a sheet what the binding is for a particular chemical, you will get a number, but that number is an average. What's really going on is some things are bound really well. Some things are let's say, well, instead of things, let's use a particular chemical. Let's say you had benzene. A benzene molecule may be bound really well, while another benzene molecule not so much so, but most benzene molecules are bound at a particular energy on average. That seems like kind of a goofy, mundane point, but it is important. So chemicals bind with Gaussian energy distribution and are therefore released from the activated carbon in a manner that balances the chemicals in solution with the chemical bound to the activated carbon. So it's a balancing process. See, if you look at benzene on the left-hand side of the screen, the benzene concentration in solution may be 10 parts per million. The capacity on the activated carbon is 40 milligrams per gram of carbon, per gram of carbon, versus 1 ppm in solution versus 1 milligram a gram bound. And you can see how it varies depending on the concentration in solution versus the concentration on the carbon. And activated carbon maintains this balancing act. Now, what determines how well something binds to activated carbon? It's the chemical structure. So if you have multiple rings, they bind better than, say, a single ring structure. Multiple double bonds bind better than single bonds. More complex structures tend to bind better than less complex structures. So a carboxylic does better than an alcohol. Iodine does better than chlorine, but fluorine does worst of all. So that gives you an idea of how you can kind of predict what molecules will bind to the activated carbon and in what manner. So carbon grinds, this is kind of a big topic in carbon remediation. If you look at the carbon, it has different sizes. GAC, or granular activated carbon, is from about 180 to 101 micrometers in size, where powdered is between 100 and 10, and the colloidal, I've got it between 10 and 2. Most of the companies advertising it will say that their average is 2. So that gives you an idea just of classification. There's not really much to learn there. Now, if you're using a colloidal carbon, let's think about some of the characteristics. Colloidal suspensions are aided by dispersants, and that's important to consider. When you have particles that are 2 microns in size, what they tend to do is clump. So you need a dispersant to keep them from clumping. In fact, the picture on the right-hand side of the screen is some colloidal carbon that's mixed with bacteria. The bacteria are green, the colloidal carbon is black, and you'll see they're roughly about the same size. You'll also see that the colloidal carbon is largely clumped. It's difficult to keep it from clumping, so that's what the dispersant's for. The idea with the small particle size is that it can be injected at low pressure, low flow techniques, where the pump pressure is intended to be adjusted to avoid exceeding the formation's fracture pressure. So that's the goal. And the amendment is intended to follow those existing pathways. The rate at which the colloid will actually agglomerate and fall out in the formation is dependent upon the dispersant employed, and different companies are using different dispersants. And the dispersant itself is exceedingly important. It influences how the colloidal carbon will distribute, its actual interaction with the formation, bioremediation rates, whether the dispersant is something that the microbes like for food, and ultimately the sustainability. So each of those would be considered. So if you were looking at a colloidal carbon, you would want to ask yourself, well, what's the source of the carbon? Oh, what's the dispersant? And finally, something more near and dear to you guys' hearts, what's the actual geology? Is this a geology where a small particle would be advisable as far as attaining distribution? Slurries. Slurries are larger particles. So if you have a GAC or powdered activated carbon, that's going to, in solution, will become a slurry. And in order to get a slurry in the ground, you typically have to jet it into the subsurface. It's called high pressure injection and is commonly used to put slurries in the ground. Initially, you'll form some secondary porosity. After that secondary porosity, then the injectate tends to follow pre-existing low resistance pathways. The injection pressure and flow rates are primarily depend on the geology itself and the injection fluids. And where will the carbon settle out? Usually in 3 to 5 meters. Efforts to try to get beyond 6 meters are not usually very successful. And how do you put it in the ground? Well, you would structure a grid like the red dots that I have here on the right-hand side of the screen, a triangular grid. The distance between them would be, 5 to 10 feet. I usually prefer like 5 to 7, but, different settings, different goals, different amount of contamination. This is all adjustable. So that's the horizontal. In the vertical, you try to inject so that the vertical injection points overlap in a staggered fashion. And these individual injection points, 18 to 24 inches apart from the top of the injection to the bottom. So you'll generally inject top down. If you do bottom up, you're kind of filling the hole behind yourself and waste a lot of material. In bedrock, you can understand why it would be different. What does the injection pressure curve look like for one of these jetting exercises? So if you use a positive displacement pump with a bypass valve, you can maintain a constant pressure, because really what you're looking for is to have your flow rate independent of pressure. You are trying to, in a sense, fracture initially, but you're not in any effort. This is not an effort to explode the subsurface or something. So this particular picture on the right-hand side of the screen is a signature from an injection in clay. And what you will see is initially the gauge pressure jumps way up and the flow is low. But then the gauge pressure drops and the flow starts to even out, in this case to about 35 gallons a minute, and the pressure drops to about 340 psi until you get to the end of injection. The exact numbers here will vary depending on geology, but this is what the curve should look like. So again, you're not just tearing things up, you're just opening up a space to start moving into the existing geology. And what does that look like? Well, here's a picture, and this particular injection is up in the Vado zone. Probably wasn't necessary, but this was, once it was excavated, we could see it. And if you look at the orange line, you can kind of see the carbon below that orange line. It's a long, flat disc. Similarly, the yellow line, you can see the carbon roll around, and then you have the two red dashes where they found some sort of existing pathway and moved up into them. This is 1.2 meters across. This is quite a distribution. This is typical up in the Vado zone. Now, of course, what's more important to most people is what does it look like in the aquifer? So this is fine grained clay, and these are 5.7 centimeter sleeves, or your 2.5 inch or 2.25 sleeves. And if you look on the left, you can see the carbon distribution pattern, how it branches off. The middle picture, I've got it marked where we've got about 1.197 millimeters as far as this fracture goes. Very, very small fracture, very fine in the clay. I've got the little guy here in red because I can see a carbon fill here that looks like that. And the reason it looks this way is because as it's branched out, it's branched back away from you, and then it's branched side to side, and the guy's head is a branch that's headed straight at you. Now, typically, when you look at the carbon in a more macro view, just kind of hold it in your hand and look at it, you might see a pattern as on the far right. Again, depending exactly on the material you're injecting into. The carbon-based injectates, such as the Boss 200, Boss 200 Plus, will intercalate between textures in the saturated zone. And you can see the carbon here, how it found that white sand lens and kind of run through it where you have clay above it. Here's another similar picture of the intercalation between fine sands and clays. And you can see the black lines are the activated carbon. And again, you can see that these are very fine lines. And the reason I'm showing you these is because oftentimes you do see the pictures of the very large carbon seams and insertions. But what eventually happens is as that large seam goes out, it begins to break and branch, and it branches into smaller and smaller and finer branches. And I wanted you to see that. Now, if you're injecting in sand, you're going to try to, it's different. You have a different pressure pattern. You have a different way in which you set up your tips, your pumps, and everything else. But the idea is to roil that sand, to basically churn it. And this is what sand would look like if you pulled a core from it, post-injection. So injection considerations. Injectate distributes is largely controlled by the soil matrix or the stratigraphy. Injectates without regard to the installation method distribute asymmetrically. Everybody always wants to tell you that they can, get it right where they need it. It's not really true. You can kind of, but geology determines. This is not strictly an activated carbon issue. The flow paths that offer the least resistance are those that are going to be followed, assuming that you can actually push into them. Anticipate, and you should anticipate mobilization of contaminants when you do an injection into a contaminant impacted area. You can't mobilize what's not present. But if it's there, think about it. You're putting mass in, you may well get mass out. If you do mobilize contamination of which you were unaware prior to that injection, what this really is an inadvertent further characterization. And as a rule of thumb, for sites that have demonstrated monitoring well concentrations for benzene greater than 5 parts per million, or soil concentrations greater than 300 parts per million, don't be surprised if you see free product. This is a generalization, but it's useful to have a rule of thumb sometimes. All injectates impact monitoring wells. Sometimes you'll have someone who'll tell you that they'll have a presentation and they'll say the other guy's stuff impacts monitoring wells, but ours doesn't. It's irrelevant. It's crazy. If you're injecting hundreds and thousands of pounds of material into the subsurface and you don't impact a monitoring well, you should probably consider that the injection hasn't distributed very well. So if the injectate does not impact a monitoring well, the distribution around that monitoring well may be poor. A monitoring well's data post-injection may not be drawn from the same pores and pathways as a monitoring well's data prior to injection. Again, this is not product specific. It's not even methodology specific. If you put mass into the ground, you're going to change things. So you need to make sure that post-injection that you give the wells enough time to both restabilize, and you need to determine what they're going to tell you. It may be different. So regardless of what product you want to use, the installation approach must be appropriate to the media to be effective. The injectates will follow subtle pathways that may or may not intersect with your contamination. Only a small percentage of the soil fractures at any time are hydraulically active. So there's a tendency sometimes for people to think that whatever is true in the subsurface just remains that way. Well, maybe it does in rock, at least on a time scale we're interested in, but maybe not so much in other materials. Gravity or low pressure injection is only appropriate in highly permeable soils or rock where the injected fluid migrates through pores and spaces between the soil grains or other openings, such as root holes, etc. This is most applicable to sands and gravels without significant binds. It's kind of a Darcy flow situation. High energy injection displacement enhances or creates openings in the soil that had low effective porosity, such as clays, bedrock. I should put silts there perhaps. Okay, let's talk about microbial growth on activated carbon. So these are two pictures. The one on your right is from a bench test, a diesel bench test, and you can see all the gas bubbles from the microbes on the activated carbon. The one on the right is a confocal microscope picture of activated carbon and the microbes that have grown on some activated carbon. So here's an experiment. And what we have is a soil core on your left. And then on your right, you have a confocal image of a carbon fracture within clay, just like the soil core to your left. And what do you see? You see that green is fluorescence. It's the fluorescence from the microbes that aligns with the carbon seam. The aquifer material, which is primarily clay, the area is largely dark. You do see some microbes, but not much. So this is a very interesting observation that, given, say, a clay material, the bacteria are going to grow far richer on the activated carbon than in the clay. So if those bacteria are important to biodegrading your contaminant, say your hydrocarbon, then you can see that adding carbon is going to allow you to have a much larger population of degrading bacteria. Thinking and keeping that in mind, I said, so I pulled another core and I just sliced those cores to look at the carbon, and I poured deep agarose over the top of the cores to ask a simple question. Where will the microbial growth start? Or where will it begin? Will it come out of the clay or the aquifer materials, or will it come out of the activated carbon from that experiment? And this picture kind of answers that question. The black spot in the middle of the picture is activated carbon. There are other black areas in there that are activated carbon. They also have growth in them, but they're not actually in the same focal plane. And what do you see? You see something that looks almost like a menorah coming out of the top, and that is bacterial growth from the activated carbon into the agarose media. And this is just a typical light microscope image. And this is what you see. You see rich biofilms forming on the carbon and acting as a source for microbial distribution in the media. Here's another picture. This was taken by Bertha Gillerup, and the green dots are bacteria grown on an activated carbon surface. Here on the left-hand side, you have an experiment that was set up. This is equal amounts of time. And on the clay material, I have circled a bacteria in two red ovals, so that now you can kind of see the bacteria are these kind of wormy little white looking things. And you'll notice that on the clay, there's not near as much bacteria as on the right-hand side, the activated carbon. You can see how rich it is in bacteria. Again, if the goal is to adsorb the contaminant to the activated carbon, followed by biodegradation, it is preferable, of course, that the microbes enjoy or want to live on the activated carbon and grow richer on the activated carbon for that degradation process. So here's another picture. This is an electron micrograph. You can see down in the right-hand corner that you got 5 microns in size. Now, I have to tell you, I colorized this, okay? Otherwise, it would be all, otherwise it would be all black and white. Technical issues. This is really, let me see if I can slide this up somewhere. What the hell? Okay, so the kind of red here are bacteria. This golden yellow is a different species. This is yeast. And the point of this is kind of the summary of a number of experiments I've done showing that the microbes prefer the clefts and crevices on the surface of the activated carbon more so than the surface itself. And it kind of emphasizes the importance of, having carbon of the size necessary to support microbial growth, which the smaller granules, the smaller you get, the less they do. So a GAC is better than a pack is much better than a colloidal. So the first statement is an assertion, but you can kind of believe it having seen the growth on clay, that microbial counts vary throughout the subsurface. The granularity of the subsurface material influences microbial count, and increasing the number of microbial sized pathways and niches in the subsurface increase microbial counts. And that's kind of the gist of the data I showed you from various experiments. Now, this is a quantarray. It's a summary from the Microbial Insights test. This will be from monitoring well data. And if you look at the unimpacted background versus the impacted background, that's the green triangles versus the blue squares. Impacted background has higher cell counts, and this is a hydrocarbon site. has higher cell counts than the unimpacted background. That's typical. The impacted background will also tend to have more degrading microbes. So you see the aromatic metabolism, which is on the left. In the middle is aerobic aphilic metabolism. And then on the far right is anaerobic metabolism. And then outside the hashed areas are total bacteria, sulfate reducing bacteria, and iron reducing bacteria. If you look at 5 months post-injection, you will see that all categories of microbes in the monitoring wells in a site that has been carbon injected are higher. The BSS gene here is a very typical one to follow. You'll see that a lot. It's succinate, benzyl succinate synthase. So let's look at this, because that was previous one was 5 months post-injection, no big deal, right? Well, what about 2 years post-injection? So on your far left, you see a selected control. It's a little side gradient, so it may have a little impact. The one in the middle is lightly impacted, neither treated. And the one on right is highly impacted, the selected control was not treated. The lightly impacted was treated, the highly impacted was treated, all with an activated carbon injectate, the BOSS 200 in this particular case. And what do you see 2 years post-emplacement? In the highly impacted area, you see some well-known hydrocarbon degraders, Smithella, disulfobulbus, hydrogeophagia, and Methanogex solingini, all of which are greatly increased in absolute numbers over the low impacted control. And this is important because, the more microbes you have, the higher degradation rate you're going to get. Now, I don't have time in this presentation, but the combination of the microbes that I've checked are well-known syntropy, where the products of Smithella and disulfobulbus and hydrogeophagia and Methanotrex feed one another. The basic ecological parameters change with a carbon injectate. So the CHO tells you the number of unique individuals, and you will see the carbon-based emplacement, that's the black lines, are greatly increased in the number of unique individuals. The Simpson index tells you about richness and abundance, and you'll see that it's a little bit richer and abundant. And so does the Shannon-Weaver index. I believe that's also a richness index. So they're increased over an impacted control and the control post-carbon injection. And I believe this is about 2 years post-injection. It's easy to show this kind of data in a short period after injection. You really need to kind of go out a few years to demonstrate that you're having a long-term impact. Okay, evidence of degradation is the decrease in the total volatile petroleum hydrocarbons to begin with. That's what everybody wants to see. They say, show me my monitoring wells are better. So on the left, this is benzene. And then on the x-axis, on the y-axis, you have dates. The arrow shows you the point of injection. So what do you see? As soon as you inject, boom, all the concentration or the concentrations of benzene and total petroleum hydrocarbons that we're looking at on this chart go down. That's absorption to the carbon. And then, given a little time, it bounces back up. That is a re-equilibration between the carbon and the dissolved phase, followed by a decrease that occurred over, in this case, over about 2 years, till finally, a little bit after that, you reach numbers that are consistent with no further, well, getting close to numbers that are consistent with no further action. This is a very, very typical pattern where you have the immediately downward decrease in the contaminants because of absorption, followed by re-equilibration, followed by degradation. The other thing that you can look at as a evidence of degradation is the consumption of electron acceptors. Considering most hydrocarbon sites are primarily anaerobic, you're going to need electron acceptors. So you see here the benzene level. You do the injection, the benzene crashes, it's the blue line. You see it bounce back up, just like we saw in the other graph, then slowly down as it biodegrades. But what happens with the electron acceptors? The first thing that happens is nitrate and sulfate both jump up because they've just been injected. Nitrate goes down faster as a preferred electron acceptor, followed by the slow use of sulfate. You generate gases. In this particular case, I chose to show methane and butane. I could have probably also put CO2, though it's at a different scale. And of course, gases are evidence of biodegradation. But the real evidence of biodegradation is, a stronger evidence of biodegradation is not what you see in the monitoring wells. It's really what you see from the soil. Why? It's the soil and aquifer materials that are holding, 80% plus of the contaminant mass. Depends on the particular geology you're in, but it's not a bad rule of thumb. So let's see if I can show you this. I might have to sneak up on it a little bit. There we go. Sorry about the technical issues, but here we are. So this is a site, and I have two lines. Ethylbenzene in the graph from 2016, followed ethylbenzene from 2020. This is core material. So we drilled down, pulled the cores, sampled the cores of aquifer material in 16 and 20. Now, visually, you can see that these two lines are different. But how different are they? If you go down into the middle of the chart where you see ethylbenzene, it is fourfold lower. The significance of that is 0.0009. And you see within this chart the other contaminants. And again, this is not monitoring well data. This is data from the aquifer material itself. There are 99 points on that chart. You see the benzene is 3.6-fold lower, toluene 1.5, etc. So now I'm going to emphasize what a p-value means so you can see why I make a deal of that. Let's say you have a p-value of 0.001, which would be, consistent with, say, toluene or ethylbenzene. That means that if the pre-injection aquifer material, the 2016 date, equaled the post-injection concentrations, the 2020 date, then you would have a 0.1% chance of getting values as extreme or more extreme if the difference was due to chance. Another way of saying it is, you looked at it, there's a difference. There's only a 0.1% chance that difference was mere chance. Thus, the real core of cleaning up is removing that material from the 80%, the aquifer material that holds it. This final chart is carbon-13 enrichment. And the way this works is carbon-12 in molecules is preferred by biological enzymes over carbon-13. So let's say we have two molecules. Benzene A is carbon-12. Benzene B has a carbon-13 in its structure. The enzyme that breaks down benzene will prefer the structure that has the carbon-12 over the structure that has the carbon-13. So biodegradation shifts the residuals to the less negative value. And you'll just have to kind of believe me in this case because we don't have time to go over it. But enrichment is from the negative 30.5 up gradient to the BOS 200 emplacement, which is the negative 27.1. That enrichment is greater than 2 parts per thousand. That corresponds to about 60% benzene degradation. The 2% is kind of a rule of thumb number. If you're that far apart, you got it, so to speak. It's not really quite that simple, but that's one way of looking at it. The upgradient wells were impacted, but they were not treated. Volatilization, dissolution, absorption, all of this do not preferentially alter the isotope fraction, or if they do, it's not significant enough to notice. It is the enzymes that determine the difference. So what I've tried to show you today is that activated carbon is a unique substance, that all activated carbons are not the same, that you can install activated carbon in the subsurface, and that activated carbon actually becomes a kind of home for microbes, increasing microbial counts beyond that the native soil could actually carry, resulting in degradation that drops the concentration in the monitoring wells, that uses up the electron acceptors that are provided, that produces gases consistent with biodegradation, and finally actually impacts by cleaning the aquifer materials themselves, resulting in a decreased concentration in those materials, and that is backed up by carbon isotope data. Thank you. I appreciate you enduring this. I hope that for those of you who are at home, that are in the office, that the screen was large enough for you to see, especially with the electron micrographs, which are really a lot of fun when you can see them well.
Thank you, Ed, for that really interesting talk on activated carbon. I have to step onto another call, so I'm going to turn the Q&A portion over to you and to Wendy to run. I'd ask that folks put their questions in the webinar chat, and either you or Wendy can find them through the chat function. Wendy can help you out there. But I do have to be on another call. Thank you again so much, and thank you to all of our attendees. One of the questions I did see very quickly was that asking if the slides can be made available. Ed, we typically leave that up to you since it's your intellectual property, but when we do make them available, we make them available to members only, so they would have to log into their account behind our behind our membership wall to ensure that your intellectual property remains yours.
Oh no,
with that, I'll turn it.
Yeah, that's no problem. I'll be glad to let you guys have the slides.
Well, with that, I'll turn this over to you and Wendy, and I will step off to my next phone call.
Have there been success? Has this been successfully used with chlorinated products? I didn't discuss chlorinated products so much today. Some of the pictures, a couple of the pictures were from chlorinateds, but yes, there is and I don't mean to be a product hawk on a AIPG webinar, but we have a product called BOS 100 and CAT 100, which are specially designed for chlorinated products. The deal is you want to get the contaminant inside the carbon, and you want to have the treatment right there internal to the activated carbon, which is true for the Boss 100. So yeah, the general process has been used with chlorinated products. And okay, how effective is activated carbon on DNAPL? Well, this is a really interesting topic because you can put a lot of activated carbon into DNAPL and you can absorb it. But to absorb all DNAPL with activated carbon becomes kind of an expensive process. But because activated carbon recycles itself, you can stabilize with the activated carbon, and then given time, it will degrade the DNAPL. The Boss 200 Plus is particularly designed for that, and we've injected in DNAPL many times. Though I should add, in all fairness, because you guys are not clueless, if you can remove that LNAPL prior to injection, that's oftentimes a more efficient approach, though there will be LNAPL even after removal that you just don't know about. So. Okay, so the other question I have here is from Doug Hess. I'm kind of getting warmed up now. I can actually know people's names. Sorry about that. And he asked about PFAS. Well, you might remember when I showed you further up in the slide that activated carbon doesn't bind carbon fluorine as well as, say, carbon iodine. It's the only one within that chart that is not consistent with the periodic table. And it has to do with the size of the fluorine molecule and the carbon backbone. In short, activated carbon will bind PFAS, but it doesn't bind it as strongly as we would like. And I have a concern that essentially that by using activated carbon on PFAS, that you're essentially making this is kind of an over-the-top statement, but I think you'll understand what I mean. It's almost like an unpermitted hazardous waste landfill. I mean, you've bound it kind of, but not really, because activated carbon maintains an equilibrium. That's why you really want to use activated carbon with some sort of degradation process, which is true of all the RPI products. And since there's no good degradation product for PFAS, the best way to use activated carbon is in above ground, and then you can send that activated carbon back to be recycled thermally. That's the wisest way to use it. Now, if you end up absorbing PFAS to activated carbon while you are, say, dealing with a chlorinated solvent, well, that's okay. That's inadvertent. But simply saying I'm going to use activated carbon in the subsurface for PFAS is probably, I think it's unwise. It's unwise.
So Ed, I don't know if you can, if you go to Chris Mata, he wants to ask a question. He's got his hand raised. Since I got knocked out, I can't unmute him. Maybe if you can go, if you sit on top of his icon, can you unmute him and he can ask his question?
Yes, I see.
Okay.
Chris, go ahead. Wait a minute.
He just has to unmute himself and now he should be able to. Chris, can you ask your question? Or is he unmuted, Ed? Sorry, I can't help you with that. I got knocked off of the co-host option when my system froze out.
Okay, Ed, can you hear me now?
Oh, I can.
Yes.
There you go.
Oh, thank you. Thank you very much for persevering. There's a little bit of debate, at least here in the wonderful state of New Jersey, as to whether or not injection of powdered or colloidal carbon is considered, I'll use the word permanent, permanent alteration to the aquifer matrix, such that with a sufficient amount of monitoring, maybe over the period of half of a year or a year or so, demonstrating achievement of standards, if we can then walk away, or if the regulators might have an expectation that things could change in the future, whatever time frame that is, such that additional injections may be required. Do you have any thoughts on that?
Yes, yes. Okay, so we would have to kind of think about each contaminant. So let's say we're talking about a hydrocarbon site, first of all. You have monitoring wells. Post-injection, you may actually install a few others that happens, or rehabilitate some of them that were already in play. And post-injection, you have that carbon there. It is an absorbent. It is not going away. It will continue to function as an absorbent, if nothing else. So that the area around those wells, the area that has been injected, is fairly stable in that structure. So if your monitoring wells are good, you're probably good. The next point of wisdom would be, at least not on every site, but most of you would want to know that you had a biodegradation process going. If you're confident in that biodegradation process, you're confident in the wells and the fact that they're trending downward or have become flat at a concentration you like, then you should be fine with closing the site. I'll be honest with you, I probably closed close to 150 or more in the state of Kentucky like that. And as far as I know, as of this date, and it's been 4, 5, 6, 7, about 7, 8 years, none of them have come back. So, it's consistent with the mechanism to close the site once you've established that you've met your goals. Now, I wouldn't say that for PFAS, by the way, because the carbon doesn't have the same binding. Chlorinated solvents, you're going to see the degradation products so clearly. You should be seeing a lot of ethane and things like that, which give you a good confidence that you're headed forward to lower and lower numbers.
Thank you.
All right. Ed, do you see that question from Doug?
I do.
Okay.
I'm reading it now.
Okay.
Okay, I know that it can be effective for PFAS removal and have used it for groundwater remediation as part of an above ground treatment system with thermal desorption for the ultimate destruction. But with PFAS soon becoming a hazardous substance and some companies marketing colloidal carbon as an accepted remedial method for PFAS, I'm wondering what your experience is with using subsurface applications. None. We don't do it. We don't do it for all the reasons that you've said above, that the best thing that could happen for PFAS at this point in time, given the technology we have, is that you do exactly what you did. Pump it out of the ground and go have the carbon thermally treated. Make it go away forever. When and if we ever come up with a good, solid degradation mechanism to pair with carbon, well, then that would be more appropriate at that time.
Okay. Well, does anyone else have any questions? I know we went over, but we started a little bit late, so we wanted to give everyone an opportunity to ask questions. And Ed, we appreciate you staying on extra for us as well.
Well, I appreciate you not broadcasting to everybody how I cried when my slides wouldn't come up appropriately.
I think it's a technology challenging day because it looks like we lost Kathy and I got locked up. It's just one of those days. We appreciate you doing this presentation for us today. Let's see. Thanks so much, Ed. Fun times with technology, right? Yeah. So, Shauna, thank you. All right. Well, I think then we will go ahead and end the webinar today. Again, Ed, thank you for presenting for AIPG Lunch and Earn. We appreciate that. And we will put the slides up. If you want to send me the PDF, we will get that up on the members only resources webpage. And thanks everyone for attending today.
Okay, well, thank you. I appreciate you guys' time.
All right, thanks, Ed. So Ed, I think you are the host on here. If you want to stop the recording, you probably see a button that says stop recording because we've lost Kathy too with technology. There, okay. All right. Wow. What a day. Let's see. Well, mine says it's still recording. Let's see.